The first example is to simplify this capacitor network. Let's have a quick review of how to simplify the resistor network. If we have capacitors in parallel, the total capacitance will be equal to the summation of capacitance of all these capacitors. Let's call them Ci. And if in series, and we have a 1 over C is equal to the summation of 1 over Ci's. We'll just use this conclusion to help us to simplify CT. Simplify this part first. We call it a block 1. And the capacitance for this block 1, we have a 2 and a 4 in parallel. So the total is 2 plus 4, right? In series with these 3. So the way to calculate that is the same as how we simplify 2 resistors in parallel. So we have 2 plus 4 times 3 divided by 2 plus 4 plus 3. So that is 2. It doesn't have a unit. So if it doesn't have a unit, we'll just keep it that way. So we simplify this part. And on the right hand side, we have a 4 and a 4 in series. So we know that is 2, right? So in this block, we have 2 branches in parallel. This branch, we just did a calculation, which is C1 is 2. 4 times 4 over 4 plus 4, right? And if you are very familiar with the way how we simplify resistor network, you know that is 2. And this is in parallel with this block 1, which is 2, so that will give us 4. So that's how we calculate the overall of this block. And this whole block is in series with this 3, so that's how we calculate the CT. CT is equal to 4 in series with the 3 times 3, 4 plus 3. So that's how we get a 12 over 7. So this is how we simplify a capacitor network. And what if I give you a very complex network? Are you able to simplify that? So you can use the same method that I taught you from chapter 2, where you can label the nodes and draw the equivalent circuit network before you simplified it. Let's look at the second example to simplify this inductor network. Let's look at the connection. So this 2 in series with this 1 in series, this whole thing. And over here we have 3 branches in parallel. Then these 2 branches in parallel. Then these 2 blocks are in series. So let me write it down. For inductors, the way to combine them is the same as what we did for resistors. We'll simplify this block by block. So let's simplify this part first. So let's call that L1. So L1 has 3 branches in parallel. 3 in parallel with 18 in parallel with 4 plus 5. 4 plus 5, that is 9. And this is 6 in parallel with the 3, that is 2. So we find that L1 is equal to 2. The unit is millihenry. So that's how we simplify the first block. And we can do the same thing for the second block. Let's call this the second block. L2, we have a 12 in parallel with 6. So that is 4 millihenry, right? Then we'll do everything all together. So we find that LT is equal to 2 in series with 1, and in series with L2, and in series 1. So 2 plus 2 plus 4 plus 1, that is 9 millihenry. So that is how we simplify this network. So last example, we're going to find a relationship between the output and the input. So over here, so this is exactly the same as what we had from the example. But in that example, I didn't talk about the details. So we have 2 op-amps. It means that we need to do it one by one, like what we did before, right? So for this first op-amp, op-amp 1, let's call this op-amp 2. For the op-amp 1, the input is V1, and we didn't define the output, so let's define the output as a V3. So I will skip a little bit in terms of how to label the nodes, and you know that this node is called V minus, and we're going to use our convention. When you work in exam, I do expect you to draw everything, but it takes me a little bit of time to draw everything in details, so I would prefer to spend a little bit more time to explain the process. The first step, we're going to do the analysis of the first op-amp. And for the first op-amp, we use the ideal op-amp model. So we always need to say that. Use the ideal op-amp model. That tells us V plus is equal to V minus. V plus is equal to V minus. So let me just level it on there. We know that V plus is equal to V minus, and I plus is equal to I minus is equal to 0. And over here, since V plus is connected to ground, which is 0, and we know that this node have a nodal voltage of 0. And then we will write the equation at this node. And the current leaving this node, or the current goes into this op-amp is 0. So we'll do that. So the current goes into this node through this branch can be calculated by using V1 minus 0 divided by R1. And the current goes into this node from this branch, which is C times dV dt. So let me tell you one place that a student like to make mistake every semester is over here. It's about what is V. And in this case, it's not that bad because it's a V3 minus 0. So you can just write a V3 minus 0. You can neglect minus 0 because that's the same thing. But when this is not 0, I already see students write a V3. That is wrong if this is not 0. If this is not 0, remember you need to use a V3 minus that nodal voltage, whatever it is. So the current goes into that node adds up to 0 because the current leaving that node is equal to 0. So this is our first equation. From this equation, we'll be able to find the relationship between V3 and V1. So V3, we put this term to the right-hand side, that will carry a negative sign, and we divide it 1 over C to the right-hand side, so it will become negative 1 over R1 times C times the integration of V1 dt. So that is how we find the relationship between V3 and V1. Next step, we're going to analyze the second op-amp. Step 2, for the second op-amp, we're going to use the ideal op-amp model, the same thing. Over here, V plus sign is connected to the ground, which is equal to 0. So it implies V minus is equal to 0. This is 0 node, right? And we'll write a KCL equation at this node. At this node, there are 3 branches connected to this node. Oh, actually, in total, there are 4 branches. One branch that goes into this op-amp, which is equal to 0, right? So let's write that equation. So we count all the current goes into this node add up to 0 because the current leaving this branch or leaving this node is equal to 0. So the current goes into this node from this branch is equal to V3 minus 0 divided by R2. So let's write that. V3 divided by R2. The current goes into this node from the second branch over here, which is V2 minus 0 divided by R3. V2 divided by R3. And the current goes into this node from this branch, which is equal to VO minus 0 divided by R4. The summation of these 3 currents is equal to the current leaving this node, which is I minus, which is equal to 0. So this is how we write the design equation. So this is how we get the relationship between VO and V2, V3. So from here, we can find the relationship between VO and V2, V3. Move these 2 terms to the right-hand side and multiply the equation by R4 on both sides. So we have VO is equal to negative R4 over R3 times V2 minus R4 over R2 times V3. So next step, we're gonna combine the conclusion that we got from step 1 and 2. Step 3, combine the previous conclusion, combine 1 and 2. So over here, we just need to replace V3 by that. And then we'll be able to find the final answer. We can move this out, and this will become plus sign. And just move this out. All right, that's how we get to the conclusion. That's all for today.